Hello everyone. Today we're going to learn about dynamic programming. This is the most confusing algorithm that students are usually confused about. And that's also one of the reasons why I started this data structure and algorithm series. After learning about dynamic programming together, you're going to truly understand what dynamic programming is and how to effectively use it in your work. Your coding is of use, and it may also make your life a better place because this is a good optimization algorithm. Today we're going to learn about part 1, the importance of depth search in dynamic programming. This tutorial is a part of the data structures and algorithms class. First, let's clearly talk about the outcomes after this dynamic programming series. We're gonna have about 10 videos for this series, and after learning about it, you're gonna truly understand what type of problem that can be solved with dynamic programming. You will actually understand what dynamic programming is and can actually apply it to solve your problems with just 3 simple steps. You'll be able to calculate the exact time and space complexity of a dynamic programming algorithm. You'll be also able to clear your mind of the myths about dynamic programming related terms that you have heard on the internet. Terms like principle of optimality, finding subproblems, optimal substructure, bottom-up, top-down, tabular approach, or tabular method, or memorization approach, also called memorization method. A lot of terms on the internet that you may not understand. And after this, you're going to be able to clear your mind and understand what they really mean. Finally, you'll be able to use dynamic programming to solve these kind of applications. Type 1, Type 2, and Type 4 problem that we have talked about before. Minimization, maximization problem, or just finding anything most optimal for your problem. Example of these problems are maximize profit, minimize cost, or choosing optimal choices. Other examples can be optimal sequence of action to achieve the best outcome. And also one of the most important thing about dynamic programming that people usually forget is simulation. Dynamic programming can be used to simulate different scenarios, something in real life, and then you can choose the best scenario based on your requirement. So these are the outcomes after finish learning this dynamic programming series. Now we do have some prerequisites before continuing learning dynamic programming. The first one is, if you knew something about dynamic programming, I ask you to temporarily forget everything you have heard about dynamic programming. And once you finish learning dynamic programming with this series, everything about DP that you knew will coming in clear. The next one is, DP requires a lot of previous knowledge. They are call stack and recursion, which we have talked about, and depth search. Depth search is an extremely important part of dynamic programming, so only proceed after you have learned these tutorials. Next, let me briefly introduce to you the modern law of dynamic programming. If you are interested in the paper, it's coming with this link by me in the year of 2023. The paper name is too long, so I'm gonna call it SESV for short. That is to distinguish my work with Richard Bellman's work on the first paper on dynamic programming in 1954. It's almost 70 years before the theory of dynamic programming. So throughout our dynamic programming series, we're gonna call the theory of dynamic programming Bellman's DP, and we're gonna call the modern law of dynamic programming Sam's DP to identify what we're talking about. Now what you're gonna learn is very different from Bellman's DP. It's still dynamic programming, but it's very different from the original author, Richard Bellman, and it's definitely very different from anything you can find on the internet up to the time of making this video. But to be clear, it's a continuation of understanding and applying dynamic programming. Sam's DP doesn't mean to replace anything. Rather, it's a supplement for you to better understand and apply dynamic programming. And everything's gonna be much clearer in the comparison table that we're gonna have by the end of this series. Now the purpose of Sam's DP stay the same and is aligned with the purpose of this course from the beginning. That is, Sam's DP purpose is to help you to pass difficult coding interviews, as well as understanding and applying DB in your daily work and life. You don't have to read the whole paper. of the modern law of dynamic programming. The summary of it is, SAM's DP is a law. It can be proven. As opposed to Bellman's original DP, it was initially called a theory, and a theory doesn't require proof. The big difference is, a law is always true. A theory can be true or false. That also means a law can guarantee you a result. A theory, it can or it cannot give you a result. And SAM's DP mainly designed for solving coding interview purposes. Secondly, it is for clearing the myth about dynamic programming. And thirdly, to introduce the importance of computer simulation to your life. And as a software engineer, it is important now and definitely into the far future of the human life. The application of dynamic programming or simulation can be found in every aspect of life. For example, finding COVID vaccine or looking for the best combination of materials for the best possible electrical batteries, and so on. So what is the modern law of dynamic programming? The modern law of dynamic programming, or SAM's DP, says that if you can describe your system as follows, a system state is comprised of a limited number of parameters that describe your state. Choices to change state is a limited no number of choices to change your system state, and you have the same choices at any state. Final states are the states that achieve your desired information, or the states where you can choose any choices to change state anymore, can reach final states. That means after a finite number of choices to change state, you can reach your final state. And your whole system, as well as the course of running your system, can fit into a computer in terms of RAM and CPU. If you have a system like this, then the modern law of dynamic programming guarantee you that you're gonna have a systematic procedure to design and code your solution. You're also guaranteed to have the best answer based on your requirement. You're also guaranteed that the time and space complexity of your solution are always equal. And the time and space complexity will be in polynomial, which is on squared, or on cubed, and so on. And finally, the time and space complexity equals to the number of distinct states created. If it confuses you, don't worry. You're gonna find everything much clearer by the end of the series. Now let's have a look at some real-life application of DP. Let's say that you are a president of a nation, and that your nation have money and choices to spend it. So what kind of activity do you choose to spend to make the most impact? That is a DP problem. Another problem is, you are a skilled worker, and you work 8 hours a day, 9 to 5, and there's plenty of tasks that are associated with different times and different rewards money, and this time frame of the tasks can overlap, so you cannot do them all. And the question is, which series of tasks should you choose to maximize your earning within your work schedule of 8 hours a day? That is the DP problem. Let's have a look at another example. Then we have a map, and we're hunting for goal. The problem is we need to travel from start to end. Start is the green dot here, and end is the yellow star here. And at any position in the map, we can only go right or go down. So for example, if we are at 0, 0, we can go right to 5, or we can only go down to 2. Same thing, if we are at 0, 1, which is here, we can only go right to 3, or we can only go down to 7. We cannot go left. And the question is, what path should we take to collect the most gold? This is also a DP problem, and we're gonna talk more about this problem later. Next, we're gonna learn about the importance of depth first search in dynamic programming. If we don't understand the important role of depth first search in dynamic programming, we will never be able to really understand dynamic programming code. For example, like this code that we have here. There are 3 recursive calls in this DFF function. The first one is here, the second one is here, and the last one is here. Is it really possible to understand this kind of code? To answer if there is a general way to understand this kind of code, dynamic programming code, we need to learn the importance of depth first search in dynamic programming. And after you learn about this, the pattern will come very clear. And when looking at a code like this, you know exactly what's happening. So to learn SAM's DP step 1, we learn that one depth first search is gonna give us one branching. We're gonna learn about it with this factorial example. But before doing that, keep in mind that depth first search helps to generate states with predefined choices. Again, the important role of depth first search in dynamic programming is its help to generate states with predefined choices. And when looking at this example, try to focus on relating the code, how the codes look like, with how the code stack look like, and how the depth first search tree look like. With that in mind, let's start looking at our first example, factorial. So in this example, we're gonna learn that one depth first search gives us one branching. Factorial of a number, for example, factorial of 3, gonna be 3 multiplied with 2 multiplied with 1, and that's gonna give us 6. So basically, factorial of a number is just multiplying itself with all the integers before it until 1, and then the result is the factorial of that number. We have seen this code before. It's very short. Here we have if n equal to 1, it's going to return 1. Otherwise, it's going to return n multiplied with factorial of n minus 1. And we're going to look at the code stack to see how this function going to create the result that we want. So when we run factorial of 3, the factorial of 3 go into the code stack, and it's equal to 3 multiplied with factorial of 3 minus 1, which is factorial of 2. But we don't know what factorial of 2 is. So this function will wait, and factorial of 2 go into the code stack, and factorial of 2 gonna equal to 2 multiplied with factorial of 1, which is what we have here. And again, we don't know what factorial of 1 is, so this function will wait, and factorial of 1 go into the code stack. And factorial of 1 that we have here gonna be 1. So we have factorial of 1 equal to 1. When this happens, the function is resolved and it will be removed from the code stack. And now we are back with factorial of 2 equal to 2 multiplied with factorial of 1, which is 1 that we know from here. So that 2 multiplied with 1 gonna give us 2. And then this function is resolved and it's got removed from the stack. And then it returns to factorial of 3, gonna be equal to 3 multiplied with factorial of 2, which is 2 that we know before. And that's gonna be 3 multiplied with 2 equal to 6. Just by the nature of the code stack and the way that we write factorial function like this, we can calculate factorial with just very minimum lines of code. It's actually only 2 lines of code here. And we can do this because the computer designed this way. The code stack is designed this way, and we can actually utilize it in the code by writing the function like this. There's nothing to be confused about this. This way of function running and the code stack running is a true fact, and you can remember it by heart. Now, do we always have to draw out the code stack to know how this function works? The answer is no. Instead, we usually have something called the recursion tree, but here we're gonna officially call it depth first search state tree, and we're gonna know why in a few minutes. But for now, this tree right here that we see is a one-to-one mapping with what's happening in the code stack. So we call factorial of 3, and it's equal to 3 multiplied with factorial of 2. So the 3 go down to factorial of 2, and it's equal to 2 multiplied with factorial of 1. And the 3 gonna go down again. Factorial of 1 equal to 1. That's where the tree stops. If we think about it, this tree gonna go as deep as it needs to reach the base case where n equal to 1 is gonna return 1. So let's say that we have factorial of 1000. This tree is gonna go 1000 nodes deep until it hit 1. And that is the depth first search node visitation pattern. It goes as deep as it can until it cannot go any further. You can see that the number of our interests are 3, 2, 1 here, which are the number we need, the number that we are interested in to be used to calculate factorial of 3, which equal to 6. And we call this number of interest our state parameter. And we call this node that we have here is a state. Another observation that we can have is, in the body of this factorial function, we only have one recursive call. And if we look at our call stack, and then to our depth first search state tree, the tree always have only one branch, from top to bottom. That is why we're calling this tree a depth first search state tree, because the pattern for the tree to run is a depth of search pattern, and when it runs, it's generating states alongside with it. You can think of a state is a node in the tree. And if we look at the body of this factorial function, we can only see one recursive call. And with one recursive call, our tree is just one way down. It has only one branch at each node. So to summarize our observation here, we have the relationship between the code with the call stack and the depth first search state tree. That is, if we only have one recursive call, at each node of our state tree, we only have one branch. And when the function runs, the call stack runs. The tree is a symbol image of what's happening in the call stack. And when the tree starts branching, it generates states. You can think of a state is a node of the tree. And alongside with the state are the state parameters, the information that we are interested that we can use to calculate our goal, our factorial number. And then if we run our factorial, it's gonna give us all the state parameter that we're interested because we console log it out here. And finally, it's return the result that we want, which is factorial of 3 equal to 6. So remember, one depth of search within the body of the function, which is this line here, is gonna give us one branching. Next, for learning SAMSDB step 2, we're gonna see that if we have two depth of searches, it's gonna give us two branchings. And the function that we're going to have a look at today is the Fibonacci function. If you might recall, the Fibonacci sequence is a sequence of numbers. The first one is 0 and the second one is 1. And the number after that is going to be the sum of two immediate numbers. So Fibonacci number at position 2, which is here, going to be the sum of 0 and 1 is 1. And the next one, 2, is going to be the sum of 1 and 1, and so on. So, and this is the code implementation of the function. If n equal to 1, we're going to return 1. If n equal to 0, we're going to return 0. And in general, we're going to return fib n minus 1 plus fib n minus 2. And Fibonacci number at position 3, we're going to return 2. And again, we're going to have a look at the call stack to see how this function is going to give such results. In the meantime, pay close attention to the number of the recursion call that we have here within the body of the function with the number of the branches that we have here in the depth of search state tree. So when we call Fibonacci of 3, this is what's going to happen in the call stack. Fibonacci of 3 equal to Fibonacci of 2 plus Fibonacci of 1. And we don't know what Fibonacci of 2 is. Then this function goes to the call stack. And Fibonacci of 2 equal to Fibonacci of 1 plus Fibonacci of 0. And here we don't know what Fibonacci of 1 is. So it also goes to the call stack. It's called Fibonacci of 1. And Fibonacci of 1 is going to be 1 here. So 1 is returned. While this happened in the call stack, we have our depth of search state tree. A Fibonacci of 3 equal to Fibonacci of 2 plus Fibonacci of 1. And so we have fib 2 down here. And fib 2 equal to fib 1 plus fib 0. So we have fib 1 down here. So this whole branch is associated with what happened in the call stack in frame 1. And this fib 1 is going to return 1 of what we have here. As you can see, this pattern of node visitation is a depth first search pattern. And if we print out the state parameter, the fifth number that we're interested in, the first depth that we have is 3, 2, 1, which is this branch that we have here. So now we have fib 1 equal to 1. It's going to return to here. And then we're going to go to call stack frame 2. We have fib 2 equal to 1 plus fib 0. And we don't know what fib 0 is. So fib 0 go to the call stack. And when it runs, we have fib 0 equal to 0. So it returns 0 here. This frame in the call stack is associated with what we have here. In the depth of search state tree, fib 2 equal to fib 1 plus fib 0. Now it's go to this branch and hit a base case. And it's returned 0. And then we have fib 0 equal to 0. And now we know fib 2 equal to 1 plus 0 equal to 1. Let's have a closer look about this depth of search state tree that we have here. You can see after the first depth, our tree, if visiting another depth, it goes all the way down to the base case and it returns 0. So we can see that even with two recursive calls in the body of this recursive function, the order of generating states or generating nodes and node visitation is actually a depth first search pattern. This is an important key information that we need to observe and remember because it's gonna help to generalize. No matter how many recursive calls that we see, the pattern of state generation and node visitation just gonna be a depth of search pattern. Now let's have a look at this node. This is a very interesting node. As this node, the last branching node on the leftmost of the tree. Again, it's the last branching node on the leftmost of the tree. This is a very special node because the first calculation of the function between the recursive calls happens here, as we can see in the call stack. This is where, in the first time, we have the information of fib minus 1 and fib minus 2, which is 1 and 0, equal to 1 here. Now we know fib2 equal to 1, and it returned to fib2 here, which is 1. Now we're calculating fib3 equal to 1 plus fib1. And we don't know what fib1 is, so we put it into the stack, and we call fib1. And fib1 equal to 1, and that's what we have here. And that is when we have this branch that is visiting fib1. And then we have fib1 equal to 1, so it's got resolved here. So now we know fib3 equal to 1 plus 1, which equal to 2. And our function is complete. Our call stack is empty, and our state tree is complete. Now if we print out the state parameter information that we're interested in, it's gonna show us 3, 2, 1, 0, 1, which is what we have here, 3, 2, 1, 0, 1. The question is this a random sequence? And the answer is no. And we can draw out our deficit state tree just by looking at the code. We know that fib3 is gonna lead to fib2 and fib1, and fib2 is gonna lead to fib1 and fib0. It's gonna print out 3, 2, and 1, which is the first depth of a depth first search node visitation here. And it's gonna print out 0, which is the next depth that we have here, and it's gonna print out 1, which is the last depth that we have here in this tree. So we can see there's a close relationship between the number of the recursive calls here with the state tree and the order of the state parameters. So basically when we see two recursive calls, we know that the deficit state tree is gonna have two branches, and we can keep branching to finish the tree until it hits the base cases. And then the order of node visitation is absolutely following the deficit node visitation, which is visiting the tree as deep as it can first, and then to another depth and another depth until it finishes the tree. This is a very important observation. The relationship between the number of the recursive calls, the tree, and the deficit visitation of the node, and the state parameter printout are closely correlated, and we can actually ignore the call stack. And remember, this is only reflecting what's happening in the call stack. So if we know that this is a deficit pattern state tree, we can completely remove the call stack. If we see a code like this, we know what's happening with the code. What's the order of the state printout? So again, our observations are there's a strong relationship between the code, the call stack, and the state tree, and of course, the parameter that we print out. The state parameters is the number that we're interested in because this number is going to help us to calculate the final result that we want. The recursion that we have here generates states. A state is a collection of parameters that we're interested in, and in our case here, we are only interested in one parameter. And finally, the two recursive call equal to two branching. So if we see two recursive call here, we know there's going to be two branches at each node or each state. And if we run our Fibonacci function, it's going to print out all of the state parameters and the final result that we want, fib3 equal to 2. Next, learn SAM's DP step 3. We're going to learn that if we have three depth searches, it's going to give us three branching as each node. And our example here is called Fibonacci. Fibonacci sequence is just like Fibonacci sequence with a really small modification, which is instead of the number is the sum of the last two number. For Fibonacci, it's going to be the sum of the last three number right before it. It's just adding more one line, which is n equal to 2, it's going to return 1. And in the return parameter, we're going to have the sum of the last three numbers, n minus 1, n minus 2, and n minus 3. So when we run this code with Fibonacci of 5, we receive 7. And when we print out n, This is what we have on the console. 5, 4, 3, 2, 1, 0, 2, 1, 3, 2, 1, 0, 2. It has a way to know what's happening and why the state parameter is printing out this way. And the answer is yes. And we know our call stack, and we know what's happening in the call stack with the two previous examples. We can draw our deficit state tree like this. Fibonacci of 5 equal to Fibonacci of 4 plus Fibonacci of 3 plus Fibonacci of 2. And that's what we have here. 5 is going to branch out to 4, to 3, and to 2. And we're going to keep branching at each node until it hit the base cases. So 4 is going to branch out to 3, to 2, and to 1. And then 3 is going to branch out to 2, to 1, and to 0. 2, 1, and 0, which is what we have here, the base cases. So it's going to stop branching. The same thing that we have here with 2 and 1. And with these two branches here, from 3, we're going to have 2, 1, and 0. Which are the base cases, so it stopped branching down. And 2 is also a base case, so it stopped branching down. So after drawing out the tree, we know this is what happens in a call stack. Now, what's the order of its happening? We already know about that. It's a depth versus no visitation order. So it's gonna go all the way down for the first depth, which is 5, 4, 3, 2, which is the first depth that we see here. So by drawing down this tree, we understand why the console printing out a state parameter this way. And the second depth is 1, and that's why we have here the second depth. The third depth is 0, which is this one. So that's what we have here. And this is finished. And we're gonna have the fourth depth, the fifth depth, which is 2 and 1 here, just what we have here, fourth depth of 2 and fifth depth of 1. And then the next depth is 3 to 2. Remember, it's always go as deep as it can to finish a depth. And that's what we have here, the sixth depth, 3 and 2. And then we have the seventh and the eighth depth. And lastly, we have 2, which is the ninth depth. So with our observation, from the code to the call stack and the tree, we now no longer need the call stack to understand what's happening when we have recursive calls with the tree and the depth first search node visitation. We know what's the order of node visitation and code execution. And remember, the last branching node from the leftmost, which is this node here, is where we have the first calculation. It can be any calculation. It can be the sum of these 3 branches, or it can be the max number or the mean number of these 3 branches, or it can be multiplication. We can do whatever calculation here. The important thing is we need to remember that the first calculation happened here. So back to our observation. Now we know how to interpret the code and see what the executions are. We also know to check if the tree we're drawing is correct by looking at the console, and vice versa. If we're designing the tree, we know if the code generating the state like the tree we draw correctly if we compare what print out in the console with the content of the tree that we have in the depth first search pattern. Now it's clear that the recursion generates the states. The state is a collection of parameters that we are interested in. And in our case, we're only interested in one parameter, n. And lastly, but most importantly, we learned that 3 depth first searches are gonna give a 3 branching at each node. We always have 3 branching at each node. So if we run our code like this, it's gonna print out all the state parameters, and the result of Fibonacci of 5 is 7. Next, learn SAM's DB step 4. We're gonna generalize the depth first search branching and cutting. The cutting is really simple. Let's say that we still have our Fibonacci function, and for this function, I'm gonna call it depth first search. I'm just changing the word here. And in this function, I don't care about the end result. I just care about generating states. So I'm not returning anything at the base cases. I just stop the branching at the base cases. And I don't even do any calculation at all. I just randomly call the recursive function. Now I'm calling it DFS. In front of each function, I'm adding a check. I'm checking if the next state is an even number or not. If it's an even number, I'm gonna run this depth first search function. If it's not, it's not gonna get run. And I'm doing the same thing with the rest of the 2 depth first search functions. So basically, if they are even, I'm gonna run them. If they are not, I'm not gonna run them. And if I run this function is gonna give me 5, 4, 2, 2, and undefined. It's returning undefined because I'm not returning anything here within the function, but y is returning 5, 4, 2, 2. And we can understand why by looking at the deficit state tree that we have here. So this tree is basically the Fibonacci tree that we had before. It looks exactly the same. The difference is I'm cutting some branches up this tree because I'm adding some logic whether I want to continue to branch down from this state or not. And I'm doing it by adding a check here. This is equal to an if condition to allow the computer to go to this logic or not. And the logic is, if the number is even, I will continue to branch. If it's not, I'm not running this deficit function. That means that it's not gonna branch. So from the tree that we had before, that's basically saying that I'm cutting off the nodes which has the uneven parameter. That is 3 here, and 1 here. So that's basically I'm cutting off this node, and this node, and alongside any other branching below these nodes. And because of that, my depth of such result is gonna be 5, 4, 2 for the first depth, which is what we see here, and that is the first depth. And the second depth is just 2, which is what we see here, the second depth. So as you can see, once we have the whole tree, trimming the branches of the tree is quite simple. That is, we're adding some logic to allow the computer to run this function or not, and then we are done. It's that simple. For cutting branches, there are 2 places to do it. The first one is on the top, where we have the base cases. The second one is in the body, where we use true or false logic to control if the computer should run the recursive call or not. And we can definitely show this logic from here to here by drawing the full tree and then applying this logic to cut down the branches. Now note that I don't even return anything here because I don't need to. All I'm caring about is part is using the recursive deficit call to generate the states and to check if the tree reflecting the code. I can compare the printout of the state parameter with the deficit node visitation of my tree and vice versa. That means if I draw a tree and I code something, I can check if my code is generating the tree that I want by comparing my deficit state tree node visitation with the printout of the code. So after 4 steps of learning SAMDP, you should be comfortable when you see multiple deficit call and to honor this role of deficit search. In understanding the code stack and the order of code execution, I highly suggest whenever you have a recursive call in your dynamic programming function, name it deficit search to make it easier to imagine what's happening in the state tree. For conclusion, after the first 4 steps of learning SAMDP, we have a pretty good understanding of deficit branching and cutting. That means whenever we see a multiple deficit call or recursive call, we can draw the state tree and understand the code execution orders. And the deficit call generates states, which is what we want in dynamic programming. The branching and cutting logic is independent with calculation logic. You can see that we have no calculation here, and we still have the deficit state tree, no problem. So they are independent, the branching and the calculation. The next observation is the number of deficits always equal to the number of branches at each node. Here we have 3 deficits and we also have 3 branching. If we have 5 deficits here, we're gonna have 5 branching at each node of the state tree. And there are 2 places to cut the branching. One is the base case that we already know. The second one is a true-false logic before the deficit call. So we can have full control of the branching. And with Fibonacci branch cut, if we run this code with deficits of 5, our result's gonna be just 2 depths, 5, 4, 2, and 2. And we're not returning anything. So we have undefined here. The true here is testing the even number logic. Now to summarize the first 4 steps that we learned, they're all about deficit branching and cutting. So when we see multiple recursive call, we should no longer be afraid. For example, when we see this kind of code with multiple recursive call within the body, we should no longer be afraid. Instead, we should comfortably draw out the state tree and understand the code execution order. So by looking at this code, we can draw out the tree and understand what's happening in this code. And trust me, that's the fastest way to understand a dynamic programming code. It's way faster than drawing out the code stack. Second, when applying this depth of search branching and cutting pattern, I highly suggest that you name your recursive function depth of search, just like this one that we have here, to emphasize the important role of depth of search in dynamic programming. We know that depth of search is going to generate states, which is what we want in dynamic programming. The branching and the cutting logic is independent with the calculation logic. Once we have the full tree, we can calculate later. The number of depth of search call always equal to the number of the branches of each node, just like what we have here. There's two places to cut the branching, which is the base cases on the top and the true-false logic to decide if we should run the DFS call within the body. Now with this information, you actually can create any kind of tree and cut the branches anywhere you want. Then you can also turn that tree into coding. Lastly, depth of search is a subject that we have learned quite intensively before. After you have the depth of search state tree, you can treat it as a graph and apply what you have learned to explore or collect any kind of information that you want. You can collect the nodes data with the depth of search pattern from top down or bottom up. Understanding the role of depth of search in dynamic programming is half of the work of understanding and applying dynamic programming. In the next video, part 2, we're gonna see how we can use the knowledge that we learned today and apply it to solve dynamic programming in a modern way. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.